In this video, we'll look at two more initial value problems. The first example wants us to solve the initial value problem y double prime minus 2y prime plus 2y equals 0 with initial conditions y of pi equals e to the power pi and y prime of pi equals 0. So the auxiliary equation here is given by r squared minus 2r plus 2 equals 0. And I'll leave it up to you to check that the roots of this auxiliary equation are given by 1 plus or minus I. So what that means is that our alpha equals 1 and beta equals 1. And so that means that our general solution to this equation is c1 e to the power t cosine t plus c2 e to the power t sine of t. Now, the derivative of this is very similar to finding the derivative in the previous video. And so we're going to use a product rule twice, and we get that c1 e to the power t cosine t is the first term, then plus c1 e to the power t sine of t, and the derivative of cosine is negative sine, so that positive is actually a minus. And then for the second part, we have c2 e to the power t sine of t, and then plus c2 e to the power t cosine of t. Okay, the first initial condition is y of pi is e to the power pi. So that means that on the left-hand side, we can write e to the power pi, and then on the right-hand side, that is equal to, and we're going to plug in pi for t here. So we have c1 e to the power pi times cosine of pi plus c2 e to the power pi sine of pi. And now the nice thing about pi is that sine of pi is 0, and so this whole term disappears. So that means that this is now equivalent to e to the power pi equals, in cosine of pi, that is equal to -1. So we have c1 e to the power pi times -1. And now dividing both sides by e to the power pi and then dividing by -1 leads us to c1 equals -1. Now the second initial condition is that y prime at pi is equal to 0. So that leads to the equation 0 equals, and now we have to plug in pi here, c1 e to the power pi cosine of pi minus c1 e to the power t sine of pi plus c2 e to the power pi sine of pi plus c2 e to the power pi cosine of pi. So note I plugged in pi for t in this second derivative here. Now again, sine of pi is 0. So this disappears and this disappears. Cosine of pi is -1. So our differential equation, or our equation for C1 and C2 now becomes 0 equals negative C1 e to the power pi. The negative comes from the cosine here. And then negative C2 e to the power pi. So now let's plug in what we know for C1. So we have 0 equals e to the power pi. Negative times the negative becomes +1 minus c2 e to the power pi. Now bring that to the other side and then divide by e to the power pi, and we get that c2 equals 1. And so our final solution is y of t equals negative e to the power t, that's our c1, cosine of t plus e to the power t sine of t. Okay, and one final example for this video, we're going to solve the initial value problem w double prime minus 4w prime plus 2w equals 0 with initial condition w at 0 equals 0 and w prime at 0 equals 1. The auxiliary equation for this differential equation is given by r squared minus 4r plus 2r equals 0. Now, I'll leave it up to you to use the quadratic formula or another method to find that the roots of this equation are given by r1, r2 equals 2 plus or minus square root of 2. Now, at this point, you might be tempted to say that alpha equals 2 and then beta equals square root of 2. However, that is incorrect. And the reason is that 2 plus or minus the square root of 2 does not have an I. So what we actually have to deal with here are two real distinct roots. And that means that our general solution is given by y of t equals c1 e to the power r1t plus c2 e to the power r2t. And when we plug in those values for r, we get that y of t equals c1 e to the power 2 plus square root of 2 times t plus c2 e to the power 2 minus square root of 2 times t. Now, it doesn't matter here what we call R1 and R2. You could also flip that here and put the minus here and the plus here. Either way, you'll get a correct answer. So, and by the way, I need to make that w of t. Right? Our function is not y here, but it's w. And in order to use the initial condition, we also need to have w prime of t. And the derivative here we can find by just using a chain rule. So the derivative of this expression is just e to the power 2 plus square root of 2t. But because of the chain rule, we'll have to multiply by the derivative of this inside the exponential function, and the derivative of a linear function is just the value in front of that t. So when we look at w prime, I can write that as c1 e to the power 2 plus square root of 2 t, and all of that multiplied by 2 plus square root of 2, right? The derivative of the inside function, and then plus c2 e to the power 2 minus square root of 2 times t times the derivative of what's inside. So that's 2 minus square root of 2. Okay, now we're ready to take a look at the initial conditions. So the first initial condition is that w at 0 equals 0. And we plug that into our w of t. So that is equivalent with 0 equals c1 e to the power 2 plus square root of 2 times t, which is 0, and then plus c2 e to the power 2 minus square root of 2 times 0. And after simplifying, we get that 0 equals c1 plus c2. Again, this whole exponent is 0, e to the power 0 is 1, so we are left with c2, and here we're left with c1. Okay, the other initial condition, w prime at 0 equals 1. So that is equivalent with 1 equals c1 2 plus square root of 2. I'm moving that factor to the front, and then e to the power 2 plus square root of 2 times 0 plus c2 2 minus square root of 2 e to the power 2 minus 2 times 0. Now again, the exponential function disappears because we're plugging 0 in, so that just becomes a factor of 1. So this differential equation now, or this equation now simplifies to 1 equals c1 times 2 plus square root of 2 plus c2 times 2 minus square root of 2. Okay, this is a system of equations, and so what we're going to have to do is we're going to have to solve this first one for either C1 or C2. I'm going to take C2 to the other side, so I get negative 2C2 equals C1. I'm going to plug that in here. So for C1, I'm going to plug in negative C2. So let me take that right here. And I'm going to plug that into my equation here. So I get 1 equals negative C2, and then 2 plus square root of 2 plus C2 times 2 minus square root of 2. And if we clean that up a little bit, on the right hand side, we're left with negative 2 square root of 2 C1 equals 1. Because you see we have a negative 2C2 and a positive 2C2 that cancels, and then we're left with twice the square root of 2 with a negative in front. And sorry, this should be C2. So we can now solve that for C2, and C2 is equal to 1 over negative 2 square root of 2, which is an acceptable answer to me, but we can also simplify this and multiply top and bottom times square root of 2. And we then get that C2 is negative square root of 2 over 4. And then going back to C1 being the negative of C2, we see that C1 equals negative of negative square root of 2 over 2, or negative 2 over negative square root of 2 over 4. And so that is square root of 2 over 4 for C1. And so now we can go back to our general solution here and fill in the values for C1 and C2. So our final solution is W of t is equal to square root of 2 over 4 times e to the power 2 plus square root of 2 t minus square root of 2 over 4 e to the power 2 minus square root of 2 times t.